Hi, grade 10s. It's Sunday. Here's your, I guess, less is more video. Like I said in class, I tried to find one on YouTube to go over the stuff that we went over last class on the board. I couldn't find one available, so I just decided to make one. So if you want to copy what I'm doing, you may want to reprint this. I've uploaded it to Edsby, and then also have a copy of the periodic table out. I know there's one in your textbook. This is the one that I used to use in school, so if you need to pause the video and get those things, that would be great. If you actually want to use your one that we made together, I'm going to try to follow the same order. Okay, so whatever is going to be useful to you. So if you take a look at our periodic table here, and my apologies, I couldn't get my ring light to work, so I have my window open. I know some of this is blurry, but I will read it as we go. So when we started labeling our periodic table in class, we started with the group numbers. Okay, so going across, I have them in blue. So it's 1, 2. These include your transition metals, and they continue 13 to 18. Okay, so I don't find these too helpful. They don't really give you a whole lot of information, but we need to know how to number them anyway. Okay, I like the family numbers instead, so I have them above in pink. So you're going to notice 1, 2, and then we're going to skip over all of our transition elements here and continue from 3 to 8. Okay, so these are way more useful and that they give you more information. So I've wrote here on the side for you to see. Okay, your family number is always going to be equal to the number of valence electrons. Okay, so what are valence electrons? Those are the electrons only found in the outer shell. Okay, so how is this helpful to us? When we're drawing our Bohr Rutherford diagrams and looking at the electrons that are involved in bonding, we're definitely going to want to know how many valence electrons each atom has. Okay, so where do we start? Okay, I've drawn here the element beryllium from the periodic table, and I can look at a couple different things. Okay, so on my periodic table, if I find the same element here, I can see a number 4 here, and sorry if it's really small. Okay, so 4, I've actually drawn it here. What is this number? Okay, it's the atomic number, and for each element on the periodic table, it's going to have its own individual atomic number, and that gives us a whole wealth of information. Okay, so your atomic number is always going to be equal to the number of protons. So I'm just going to read what I have here again because it might be a little small. So I have number, lowercase p, and then a superscripted plus. Okay, so this stands for protons. So if you're talking specifically about an atom, so you're going to notice here I have the word atom in quotations. This is also going to be equal to the number of electrons. So it's number, lowercase e, and then I have a superscripted minus sign. Okay, and that's also going to help us with the charges. Okay, so for beryllium, again, if I'm talking about the atom, it's going to have 4 protons and 4 electrons. So let's go ahead and draw that out. So if I want to include all of the electrons in the atom, not just the outer shell, I need to know some information. So again, I'm going to get my periodic table. So you're going to see me get my numbers here. And sorry if this is tilted. I have my camera hooked up to my ring light, which is broken, but I can't quite get the setup correct. But we do what we can, right? So beryllium. Oh, sorry, we're going to do sodium. So sodium on my periodic table here. Okay, it has the atomic number 11. And up here, where we were talking about beryllium, that actually tells me the number of protons. So if I want to go sodium, number of protons is 11. And I am talking about the sodium atom, so it's going to have 11 electrons. Okay, so just as a side note, if you forget, I know this was in one of our first notes. Take a look here, the maximum number of electrons in each shell. I know the first shell can only hold 2 and the next 3, are going to hold 8. So I want to keep these numbers in mind as I'm making my Bohr Rutherford diagrams. So I've got sodium. Here's my first shell. I can have 2 maximum. Okay, those are going to be separate. Remember, I'm just like a magnet. If I put 2 negative charges next to each other, they're going to want to repel. Okay, so that's why I've drawn them separate. On my second shell, I'm going to have 1, 2, 3, 4. So now I've got 6 in total. And again, notice that I've separated my electrons as I'm filling in my shells. So 6, 7, 8, 9, 10, and I need one more shell. Okay, and there's my sodium atom. So knowing what we know about elements on the periodic table, they want to be stable. Okay, so that's why we make ions, and that's why elements tend to bond to each other. So how does that work? If I know that sodium is a metal, okay, again, because if I look at this periodic table, it is here. So this is definitely a metal. And then I've drawn in our staircase, and that separates the metals from the non-metals. Okay, so metals always want to lose. So lose electrons, and then non-metals always want to gain. So we're going to go over why non-metals gain once we're done with sodium. So in order for sodium to have a full outer shell, it has to get 7 electrons or just lose 1. So what's easier, right? Of course it's going to be easier to lose 1 electron. So if you look at where sodium is on the periodic table, okay, if it loses 1 electron, it actually ends up looking like neon. Okay, so if I were to draw the ion now, so remember this is the sodium atom, so let's write atom. Now I want to make the sodium ion. Okay, my picture is going to look very similar. Okay, my first shell has 2 electrons. My second shell has 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I don't have to draw my third shell because this electron has left. Okay, it's either bonded with another ion, or it's actually went into the air or water or whatever this element is dissolved in. Okay, so sodium is pretty reactive. Okay, it really wants to let go of this electron. So if I draw it as the ion, I have to remember to include my square brackets. Okay, this indicates that yes, it is an ion, and I have to indicate the charge. So if it's lost an electron, remember I can't change the number of protons, so at the end of the day it's going to have more pluses than minuses, and it's going to have a difference of 1. So this is going to be positive 1. We don't actually write the ones in science. If there's no number, it's just implied. So if I want to not draw all the electrons, there's actually a quick way to draw this. And I know in class, and we didn't label it, but if you want to label it on your sheet now, these are called Lewis dot diagrams. And these will only show your valence electrons. And remember, valence electrons are only electrons in the outer shell. Okay, so I would have an A, and since the outer shell for Na is actually empty now, okay, I didn't even draw the ring here, I don't have to include any of the electrons on this picture. Again, because this one is gone. I still have to include my charge. Okay, so on any evaluation, we have to be really careful. Am I asking for the Lewis dot diagram, or am I asking for the full Bohr Rutherford? Okay, so let's go ahead and figure out some nonmetals. Okay, so again, our metals want to lose electrons, okay, because they want to get a full outer shell. Our nonmetals, these always gain electrons to get a full outer shell. So let's take a look at sulfur. So if I find sulfur on my periodic table here, it has atomic number 16. So that means it has 16 protons, 16 electrons. So I'm going to draw the sulfur atom. So this is going to be the unstable atom. Okay, so sulfur, my first shell has 2. My second shell, 1, 2, 3, 4, 5, 6, 7, 8. So that's 10. I need 6 more. 1, 2, 3, 4, 5, 6. So definitely not a full outer shell. Okay, I need 2 electrons. So if I want to match this up to my family number, just to give us a little reminder of that trick, okay, it is in family number 6. So there's 6 electrons in the outer shell. So looking at the family number, if I know that to have a full outer shell, I always want to reach that maximum of 8, I need to gain 2 more, and that actually matches up with our picture, right? I would gain 1 here and here. So let's go ahead and draw the ion. So I'd have S, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. That's a total of 10. And then here are my 6 to start with. Okay, this is in the atom of sulfur. Unstable. I'm going to gain 2 more. Now I have a full outer shell. Ions always have the square brackets. I've gained 2 entities that have a negative charge. So now it's going to be 2 minus. Remember, the number of protons can never change. If I want to draw my Lewis dot diagram. Okay, and it's just going to include the outer shell. So my outer shell here is definitely full. So I need to include all of those. 1, 2, 3, 4, 5, 6, 7, 8. Square bracket. 2 minus. Again, I have to include my electrons in sulfur because it's gained. Whereas over here, I have no electrons in the outer shell because my outermost electron here was actually lost. So I have essentially an empty shell, okay, sitting around the ion. I don't actually draw that outer shell in Bohr Rutherford, so I'm not going to draw it in my Lewis dot diagram either. Okay, so that's pretty much everything we went over in class. Okay, I don't want to make this video too long. If you need to watch it a couple of times, feel free. I am going to leave this posted to EDSB for the rest of the year. If you find these helpful, please let me know and I can modify videos that I find so they fit our class. I will see you in class next week. Take care.